Do we have sound? Okay, so we're rolling. So the first thing is an announcement. We'll probably get the grades up sometime later today. The TAs and I have to meet virtually and go through all of the fill in the blanks. I've corrected the fill in the blanks for in here, so that's all done. But we have to go through the electronic ones because the computer automatically picks answers from the list I've given them. But of course, the spelling is not always the same, and of course, there are other choices. And so we have to go back and check those. And so that's what we'll do this afternoon. Once that's done, we'll be able to mount the grades. And then we'll decide how many points to add. So what we're going to do today is we're going to continue on this idea from yesterday. Yesterday, we finished the discussion of axoplasmic transport, the movement of proteins inside the cell. So yesterday's discussion focused on what was happening in the cytoplasm, in this sort of tremendous volume inside the cell, which was where we were transporting proteins. We're going to move away from that now, and particularly when we get to the electrical signaling, we're going to be moving along the membrane. So much of our discussion starting today and tomorrow will be largely about what's going on at the membrane. We'll begin this discussion by another cell type in the nervous system. We'll begin this by the story of glia. Now, the glia, this name glia is derived from the Latin glue, and so the early 19th century histologists looked at these cells and said, these are the cells that are holding the important cells together. Well, there are something like 8 or 9 times more glial cells in the central nervous system than there are neurons. So they far outnumber the neurons. And as time goes on, we're seeing more and more that the glia are playing a really important role in the nervous system. They're probably even playing a role in some forms of signaling. But because we could measure electrical signaling, which is what we'll begin talking about later today, because of our abilities to measure electrical signaling, much of what we know about the nervous system is predicated on the idea of electrical signaling and the movement of ions across membranes, and the glia have really largely been lost in the shuffle. I think in the next 10 years or so, we're going to see the glia are going to be recognized as playing an ever more important role in the nervous system, particularly in various forms of dysfunction and disease. Because what the glia do, they play this really important role of maintaining the environment for the neurons. Without the maintenance of the environment for the neurons by the glia, the system can't work. The neurons are sort of prima donna cells. They can't do much for themselves at all. They're really, really good at electrical signaling, but they can't take care of themselves. And so that means there's this whole host of cells, the glia, that play an important role in maintaining the environment and maintaining the ability of these neurons to signal. And so we'll spend some time talking about that. We'll give them names. We'll talk about, in the central nervous system, we have astrocytes, oligodendrocytes, and microglia. And I'll put a caveat here. These microglia are not true glia. They're, in fact, macrophages. They're part of the immune system. It wasn't recognized until about 15 years ago that these cells are not part of the central nervous system, but are rather part of the immune system. In the peripheral nervous system, we also have glia, but they play a slightly different role. In the peripheral nervous system, we have much more room, so things can diffuse away. And so they don't play this role of regulating the environment quite so strictly. But in the peripheral nervous system, we have a different name for these glial cells. We call them Schwann cells. We're trying to get away from eponymous names in biology, and so sometimes you'll see these cells referred to as neurolemmacytes. I find neurolemmacytes to be a mouthful, so I fall back on the old name of Schwann cells. And Schwann was a guy in the early 1830s, 1840s, who initially described the cell theory of biology. And so he has a sort of an important place in biology, so he's given the name for the Schwann cells in the periphery. Now, in the central nervous system, we're going to see that the roles, well, we're going to talk about at least, for the oligodendrocytes and the astrocytes are a bit different. The oligodendrocytes are important in electrical signaling in terms that they're going to wrap insulation around neurons. They're going to form something called myelin. So their role is primarily in direct effects on electrical signaling in neurons. The astrocytes play a somewhat more indirect role. What the astrocytes are doing is they're controlling the extracellular environment. For the neurons to function properly in the central nervous system, they have to be maintained, the ionic balances in the central nervous system have to be maintained in fairly narrow ranges in the brain and spinal cord for these neurons to function properly. That's the role of the astrocytes. We need to maintain extracellular potassium concentrations in the neighborhood of 4 to 5 millimolar. We need to maintain extracellular sodium concentrations in the neighborhood of 130 to 140 millimolar. And then we also need to make sure that the buildup of neurotransmitter at these very narrow gaps between cells. Remember yesterday we drew the input regions and the output regions, where between the input region of one cell and the output region of its neighbor, there are these very narrow gaps we're going to spend a lot of time talking about, called synapses. The volume in those gaps is really, really small. And so you find that the release of neurotransmitters into these tiny volumes in the gaps can affect the concentration of neurotransmitters in that particular place. So one of the important roles of the astrocytes is to make sure that those neurotransmitter concentrations don't get too high, that we suck the neurotransmitter out of those synapses. At the same time, the astrocytes are making sure the potassium and sodium concentrations are maintained in a particularly narrow range. One of the important ideas when thinking about a comparison between the central nervous system and the peripheral nervous system is when we think about the central nervous system, we have to recognize that we have crammed several 100 million neurons inside our brain case. There's just not much spare room in there. If you ever get a chance to look at some sections in a microscope of the central nervous system, one of the things you'll recognize almost immediately is there's not very much extracellular space. Most of the extracellular space has been squeezed out so we can jam all these neurons inside the brain case. That means we have small extracellular volumes. That dictates the need for the astrocytes to regulate the concentration of ions and small molecules in those extracellular volumes. And that's largely what the astrocytes do, among other things. Schwann cells in the periphery don't have quite the same role. In the periphery, we have more extracellular space, there's more diffusion, we can allow neurotransmitters to diffuse away or have enzymes. So we don't need the glial cells to play the same kind of role in the peripheral nervous system as they do in the central nervous system. In the peripheral nervous system, the Schwann cells are primarily involved in myelination. They play the job, they have the role of the oligodendrocytes in the central nervous system. But that's carried out by the Schwann cells in the peripheral nervous system. Then I want to tell you a story about the distinction between the ability of Schwann cells and oligodendrocytes to regulate neuronal regrowth. It's really an important story for our biology, and I want to tell you a little bit about what we know about the difference in oligodendrocytes and Schwann cells in supporting neuronal regrowth. Particularly, this is where we're going to find the Schwann cells are quite good at supporting neuronal regrowth, and oligodendrocytes are terrible. And we'll talk a little bit about why that is, the molecules involved, and a little bit of why it's important for development in the central nervous system to be able to control that growth of neurons. Then we're going to change gears, and we're going to start talking about the movement of ions across membranes, the separation of ions across membranes. Remember yesterday I emphasized the idea that all of neuron transduction was predicated on the idea of ions moving across membranes. It's really predicated upon the idea of batteries and membranes. And that's where we're going to start. We're going to start talking about the generation of something known as the potassium battery. We're going to store charge, we're going to store energy across the phospholipid bilayer. And by storing energy across the phospholipid bilayer, we're going to effectively use that to do work. But that work is going to be the ability to generate and propagate electrical signals. So the first thing we have to do is describe how that battery is generated. And what we're going to do is we're going to see first, I'm just going to walk you through sort of intuitively how this works conceptually. And we'll see that there are a few main players. We're going to have the phospholipid bilayer. That's going to be predominantly impermeable to ions. So there's not going to be much movement of ions through the phospholipid bilayer. So that means we have to invoke a channel. We're going to invoke a particular channel called the potassium leak channel. Potassium leak channel is always open. So we have potassium leak channels across the phospholipid bilayer. And then we're going to do a thought experiment. We're going to put a different concentration of potassium on the outside and on the inside. It's going to be reminiscent of what we'll see in biology, but to do the numbers, I want to keep it simple. So we're going to say that on the outside of the cell, in this thought experiment, there's 10 millimolar potassium. And on the inside, there's 100 millimolar potassium. And we have a ratio. So now this is the idea of we have a potassium ratio, a potassium on the outside, potassium on the inside. In this ratio, in biology, we're always going to find the potassium concentration inside is higher, at least tenfold from what's outside. Then we're going to invoke the potassium leak channels, and then we're going to invoke a new character. These are called the impermeant anions. The impermeant anions are predominantly things like large negatively charged acid molecules. These are largely proteins and other molecules that are inside the cytoplasm. They're inside the cell. But the important and the operant word here is impermeant. They can't move across the membrane. They're stuck. So now we have this excess of negative charge on the inside of the cell. So we're going to put a potassium ratio outside to inside. Then we're going to now put negatively charged impermeant ions in the inside and ask the question, where are these ions going to go? Well, the way we set up the problem is the ions are going to start moving down their concentration gradient. They're going to move from their high concentration inside, where they're going to be something like, in our thought experiment, 100 millimolar, down the gradient to about 10 millimolar on the outside. But it doesn't take very long as the ions begin to move down their concentration gradient that these large impermeant anions with their negative charge now begin to affect the movement of the positively charged potassium. They're oppositely charged, these impermeant anions, the potassium ions, so they're now going to hold those potassium ions in place. So we reach an equilibrium, we reach a point where the probability of an ion moving down its concentration gradient is balanced by the probability it's going to be held fast, it's going to be held in place by the electric gradient. And we'll walk our way through that. So up to this point, it's all going to be just conceptual and sort of an intuitive understanding of how these gradients function. And then I'm going to make it a little bit more mathematical. I'll never ask you to solve these equations on an exam, but I think it's important to walk through this equation so you can get a feel for how the separation of these ions will affect the electrical gradient across the membrane. And this is something called an equilibrium potential. And it was sorted out in 1887, in fact, by a guy named Walter Nernst. And he was a physical chemist, and he was also working with Boltzmann at the time. And Boltzmann had figured out a lot of the statistical mechanics of how ions would move across membranes. And Walter Nernst formalized those ideas. And he said that the equilibrium potential for potassium is equal to RT over ZF times the natural log potassium concentration outside divided by the potassium concentration on the inside. This looks like a mess, all right? But it's not so bad, because when you actually break it down, these are all constants. R is the gas constant, that's a number. T is the temperature in degrees Kelvin, that's just the temperature in the environment. Z is the charge on the ion. And for our purposes today, we're working with potassium, so that's +1. And F is the Faraday. This is just a conversion of electricity, movement of current, into moles. So those are just formalities. The natural log of potassium concentration outside times the concentration inside. That's the real meat of this. And we'll convert this from a natural log to a log base 10. That's also a constant, 2.72. Multiply it times this number, and then we'll get a number which is going to be dependent upon the log base 10, the potassium concentration outside over inside. And we'll walk through some simple examples of that. That's all I want you to know. What I want you to recognize, though, is that because this is a log function, it's a log of the concentration outside over inside, it's a log of the ratio, that if we begin fiddling with these ratios, because of that log function, we're going to have big effects on the equilibrium potential. And this has biological importance, and we'll talk a little bit about that. So up to this point, we'll have set the potassium battery. We have stored energy across the membrane. But now we want to think about how we're going to use it to do work. And in order to use this battery to do work, we have to invoke another ion. we have to invoke sodium. And in this case, we're going to put more sodium on the outside than the inside. So now we're going to have a gradient in such that sodium wants to come into the cell. It's being driven down its concentration gradient. But of course, it can't move without channels. So then we'll think about putting channels in. Then we'll think about how we're going to regulate those channels. And then by regulating the opening and those closing of those channels, we can regulate the change in polarity in the membrane. We can take it from a number, which is the potassium equilibrium potential, which is usually around minus 70 or 80, switch it for the sodium equilibrium potential, which is about plus 40. So we now have an ability to oscillate between these two extremes. That's this ability now to set up something called an action potential. And the next step will be to talk about how we're going to propagate that potential from one place to another. So again, we're going to set up the battery. We're going to use the battery to do work by invoking sodium. And then we'll think about how we can move those potentials from place to place. So let's start. Let me start with a slide to summarize where we were yesterday. So this is just a simplified version of what we talked about yesterday, and this is where we ended. We had talked about the neuron doctrine. We had described the idea that the neuron is the fundamental unit of the nervous system, and we had described two ways of talking about the anatomy of those neurons. We could talk about them in a strictly functional setting, and where we said this was the cell body, it doesn't show it here, it'd be a bunch of dendrites, there was an axon and an axon terminal. And those were the very first, that was the very first nomenclature that Cajal developed, in about 1890. But we also said then that inside this exquisitely thin phospholipid bilayer, the biological membrane, is all of the cytoplasm of the cell. And that within that cytoplasm, we segregate protein synthesis in different places. Protein synthesis is going to occur up here in the cytoplasm around the nucleus in the neuronal cell body. It will be carried out both on free ribosomes and on ribosomes attached to the endoplasmic reticulum. And you remember from our earlier discussions, when we say it's a free ribosome, we're going to be generating cytoplasmic proteins. When we say it's a ribosome attached to the endoplasmic reticulum, we're going to be generating those three varieties of proteins that could be lysosomal, could be transmembrane, could be destined for secretion. We're going to be dealing with secreted proteins and transmembrane proteins. And that's what we talked about yesterday. We talked about the idea of fast exoplasmic transport using vesicles on microtubules. And we closed with a discussion of the movement of cytoplasmic proteins in slow exoplasmic transport. And the fact that what will happen is those proteins, when moving, will move at the same rate as the vesicular proteins. But they move intermittently. And on aggregate then, they move much more slowly, as much as 2 orders of magnitude slower than those proteins in the vesicles. But let's think now a little bit about the next set of cells we want to deal with. And typically, we emphasize neurons, and certainly in my training and my background, I'm neurocentric. I think about the neurons being the important players in the nervous system, but in fact, I think that this other set of cells, the other cell types which we talk about when we talk about nervous tissue, are going to be the glial cells. And the glial cells can be divided into two great categories. One will be in the central nervous system, and the other will be in the peripheral nervous system. In the central nervous system, the two big categories are going to be astrocytes. The astrocytes get their name because when the early histologists looked at them, they looked like stars to them. They have this sort of bursting pattern to them. They have a lot of points on them. So they call them astrocytes. And the other set of cells are called the oligodendrocytes. Dendros comes out of the Greek. It means tree or branch. Oligo means few. So these were cells that had a few branches on them. So they got the name oligodendrocytes. It's probably a bit of a misnomer. If you actually look at these cells in culture, they have lots and lots of branches to them. But there's a reason for this branching, and we'll talk about that a little later. Now, the third type of glial cell, which is commonly included, is something called the microglia. I never know, when I give these lectures, I never know whether to include them or not, because the microglia are, in fact, macrophages. Where the astrocytes and the oligodendrocytes have the same embryological origin as neurons, these guys are different entirely. These guys come out of the mesenchymal cell line, and so they're part of connective tissue. They're part of the immune system. And it's thought that they'll, in fact, during your lifetime, they will wander in and wander out of the nervous system. Some argument about that, whether they're permanent residents or whether transient residents. But these provide just about the only form of immunity in the central nervous system. We don't really have access, because of the tight junctions between the endothelial cells and the capillaries of the brain, we don't have ready access of the immune system to the brain. And we'll talk a little bit about that today, and why, if we do get access, it can be a problem. But normally, the only immune cells of the central nervous system are these microglia. And they're not part of the specific immune system either. So those are the main players in the CNS. In the peripheral nervous system, we'll talk about cells called Schwann cells. In some places in your reading, you may find cells called satellite cells. We're not going to talk about these. These are mostly in the ganglia and around cell bodies in the peripheral nervous system. But we're going to spend some time on Schwann cells. Now, in the central nervous system, what the astrocytes are doing is they're regulating the extracellular environment. Many people think of them as just the maintenance crew. They maintain the environment so neurons can function. Now, I think we're going to find they're more important than that. They don't just maintain things, which they do, but they also are probably doing some kind of signaling. There's probably some kind of signaling between the glial cells and the neurons that we're now just beginning to understand. And I think in the next 10 years, you'll see more of that. But what we're going to think about is this extracellular environment. Now, in the CNS, neurons are crowded together. As a detail, when you actually count cells in the central nervous system, there are something like 9 or more times as many glial cells as there are neurons. So by numbers, these are the more important cells. But again, as I said in the introduction, because we understand neurons primarily through our ability to measure their electrical signaling, we emphasize neuronal characteristics and neuronal signaling much more than glial signaling. But I don't want to shortchange what these guys do, because in this crowded environment, there's little extracellular space. Because there's little extracellular space, the role of the astrocytes is to regulate extracellular ion concentrations. And neurotransmitter concentrations. We're going to talk about neurotransmitters quite a lot The neurotransmitters are these important chemicals that are the signaling chemicals. They're the ones that open the ligand-gated channels. But for now, just recognize that if we think about a neuron, let me draw a neuron. One of our pineapple neurons. At the very end, there are going to be these regions that are going to branch out. This is the axon terminal. And those axon terminals then are going to become into very close apposition to the input region of a neighboring neuron. There's always a gap between these two called a synaptic gap, sometimes known as a synaptic cleft. So if we draw these two membranes, we'll draw this membrane here as the input region, keep that in blue, and over here we're going to now think about the output region. And this space between is called the synaptic cleft or gap. It's extracellular. And as we mentioned in passing yesterday, what will happen on this output region as synaptic vesicles will fuse with the membrane and release their contents called neurotransmitter. The function of that neurotransmitter is going to be to bind to receptors. I'll just label this as a neurotransmitter, NT receptor. And the function will be for the neurotransmitter to bind to the receptor, open a channel, and cause an electrical change in the postsynaptic cell. But what we want to think about now is the fate of this neurotransmitter. The neurotransmitter goes out into the cleft. There may be hundreds of these receptors, maybe even thousands of them. And so now there's the potential that this neurotransmitter can bind to the receptor, but there's also potential it can come back off again. So there's potential in this exquisitely narrow volume. This is only about, 20 nanometers, maybe 30 nanometers, probably closer to 30. And in this confined space, the concentrations of neurotransmitter can build up depending upon the activity in this output region. If the neurotransmitter builds up high enough in these spaces, I think you can see that we can overly activate these receptors. So one of the things we need to do is we need to regulate the amount of neurotransmitter that gets built up in these clefts. So what we're going to do is we're going to take another cell type. I'm going to show this in orange. I'm going to show it in 2 dimensions, but in fact, these processes of astrocytes the processes of the astrocytes will envelop the whole synapse. They'll run all the way around the synapse. And what their role is then is to take the neurotransmitter and transport that neurotransmitter into the glia. So astrocytes have the role of removing neurotransmitter from the synaptic cleft. So that's one of the regulatory functions. If these astrocytes are not working properly, we can build up concentrations of neurotransmitter in the synaptic gaps to the point where they dysregulate the receptors. So it's important for these guys to continually being involved in the pumping of neurotransmitter from the cleft into the astrocyte. But the other thing they do is that one of the things we're going to find is that we have to have concentration gradients. We're going to talk about that more later. But typically, in and around neurons, the sodium concentration on the outside is about 140 to 130 millimolar. This is on the outside. The potassium concentration on the outside is typically in the neighborhood of 4 to 5 millimolar. If we look at the concentrations inside the cell, on this inside side of the plasma membrane, the sodium concentrations on the inside, so we denote by sodium sub I, are in the neighborhood of about 10 millimolar. And the potassium concentrations on the inside are in the neighborhood of about 110 millimolar. These concentration gradients are going to be now useful, going to be essential for the signaling of neurons. Without these gradients, these neurons can't signal. These gradients need to be maintained at these levels pretty constantly. So the other role of the astrocytes is the astrocytes regulate ion concentrations. In the extracellular space in the CNS. So in the brain and spinal cord, one of the functional roles of these astrocytes is to make sure that these ion concentrations are maintained within these boundaries. 130, 140 millimolar outside for sodium, 10 millimolar inside. Potassium concentration is in the neighborhood of 110, but 4 to 5 millimolar outside. So that's their role. So we can think about, when you think about astrocytes in the central nervous system, think about them as maintaining the environment for neuronal function. If the environment in this restricted volume of extracellular space in the brain and spinal cord, if that set of ions gets out of regulation, then the whole system breaks down. So what I'm saying is the astrocytes are essential for maintaining the environment for neurons to function regularly. That's their job. Now we're going to find they do some signaling things too, but basically that's their job. And without the maintenance role of the astrocytes, these neurons, whose major function is to do electrical signaling, can't do much of anything. They just become broken. And so the astrocytes keep them in a functional state. But if we go back up to the upper panel, you'll recognize that there's another cell type called the oligodendrocyte. So let me start thinking about what the oligodendrocyte does in the central nervous system. Now, if you get down into the weeds, you start reading the original literature, you're going to find the oligodendrocytes probably play a role in regulating, to some extent, ionic concentrations as well. But we're going to think about the oligodendrocytes mostly as forming insulating layers around the conductal process. So when we think about the oligodendrocyte, function, what the oligodendrocyte does is it forms insulating wraps called myelin around axons, you can read conductal regions. Of neurons. What I want to do now is I want to think a little bit about how these oligodendrocytes play this role, how they perform this function. So what I'm going to do, I want to leave the Schwann cells in the peripheral nervous system for a little later. I'm going to draw an imaginary axon. We're going to look at it in 2 dimensions. And the membrane of this imaginary axon I'll label in black. And then what we want to talk about is how the oligodendrocytes form these insulating layers. So this circle is meant to be, this is the plasma membrane of the axon, sometimes known as the axolemma. And in here is axoplasm. That's the cytoplasm of the axon. So if we go back up to this image, it's as though we've taken this conductal region out here, like my arm, turned it at right angles, and now we're just looking at the circumference of that axon. That's what we're showing up above. Then there's another player, and this gets set up during development. And during development, there's going to be another cell type out here called an oligodendrocyte. And during development, what the oligodendrocyte will do is it will send out a process, an extension of its plasma membrane. And it will then contain inside the cytoplasm. So there's the neuronal cell body. I'm sorry, this is the cell body and the nucleus of the oligodendrocyte. This is an extension of the oligodendrocyte. This blue is meant to be the plasma membrane of the oligodendrocyte. And when the plasma membrane of the oligodendrocyte contacts the plasma membrane of the axon, they stick together. There's also probably some signaling in here that's going to tell this oligodendrocyte to continue growing. So what we'll see if we look at this over time, so this is going to be like a time lapse. Right, here's another image of the same axon, but it's a little later time. And so at this point, the oligodendrocyte has sent a process, goes all the way around the axon. The oligodendrocyte has circumnavigated the plasma membrane of the axon. It's going all the way around it. But it doesn't stop there. When it reaches this point where the oligodendrocyte had initially contacted the axon, it insinuates itself between the axonal membrane and the membrane of the oligodendrocyte. So that image looks a little like this. So it's the neuronal cell body. I'm sorry, it's the cell body of the oligodendrocyte. It's sent a process around. That's the initial process. But now this process continues. It's the growing end here, the growing tip, continues to be attached to the membrane of the axon, and it inserts itself between the membrane of the axon and the membrane of the oligodendrocyte and grows around again. It can do this several hundred to a few thousand times. So over and over again during development, the leading edge of the oligodendrocyte crawls around the axon and leaves behind its 2 plasma membranes. See if I can draw this as though it's continued sometime farther. And bear with me, because I often make this some kind of impossible Escher drawing by the time I'm done. So there's the leading edge. put some space. So this is the original cell body of the oligodendrocyte. Now let's find our way into the cytoplasm and walk our way back. So here's the cytoplasm. I'm going to draw it in orange. So this is the cytoplasm. It's always a question of whether it's going to come out right. Yes, it's going to work. So the cytoplasm is continuous, round and round. Each time the oligodendrocyte circumnavigates the axon, it leaves behind two plasma membranes, right? One on either side of the cytoplasm. Then in the process of myelination, much of that cytoplasm gets squeezed out. Ends up being something called compact myelin. But this process is called myelination. And the myelin is nothing more than the plasma membranes of the oligodendrocyte. Now, effectively, what we have done, it's a bit of an exaggeration, but you can imagine if this were an electrical system, you could think of this as being a wire. And you could think of the oligodendrocyte as laying down insulating electrical tape, going round and round and round. But in a biological system, each time it goes round, it lays down 2 layers of insulating tape. It's pretty much what's going on here. And so this is now how we generate these insulating layers of myelin. Now remember what the myelin is made of. The myelin is a phospholipid bilayer. Because it's a phospholipid bilayer, it makes a pretty good insulating layer. It's pretty resistant to the movement of ions. There are not many ion channels across this membrane. And so what we have now is layer upon layer upon layer of phospholipid that's generating a kind of insulation between the axoplasm here, the axon membrane, and then the outside world, because this is wrapped and wrapped and wrapped around the axon. So any questions on how that gets done? Yes?
You're saying that it leaves behind 2 plasma membrane. It's not touching the axoplasm we were just talking about.
No, it does not touch the axoplasm. It only touches the axolemma. So it contacts the axolemma. And so that's what I was trying to show here with the blue and the black lines. Those always stay separate. There'll be proteins that link them, but these will always stay separate. But then each time it goes around, because it's surrounding cytoplasm with the plasma membranes, you leave behind 2 plasma membranes. One on this side of the cytoplasm and one on the other side of the cytoplasm. So it gives rise to the 2 plasma membranes. So, and because we have continuity then, all the way back to the normal cell body, we have layer upon layer upon layer of these plasma membranes that were laid down by the oligodendrocyte. Right? Yes?
You're saying it's left behind? Does the cell die and leave?
Okay, great question. When I say it's left behind, I simply mean that this doesn't continue growing. Eventually, you stop growing, and it's fixed in time. But this will retain its connection to the living cell body of the oligodendrocyte. There's probably even some movement of proteins from the oligodendrocyte cell body through the cytoplasm, but not very much, because much of that cytoplasm has been squeezed out as it wraps itself round and round the axon. But no, I don't mean to imply that this cell's dead. It's that throughout life you'll maintain that connection. Yes?
How long does it take to complete that myelination process?
Well, the myelination process, this process itself during development, I don't know exactly, but the diameters here are not very big. We're talking a big neuron being 3 micrometers, 5 micrometers. And so we'll let you do the numbers, pi d, if it's, say, 2 micrometers in diameter 2 micrometers in radius for a 4 micrometer axon, pi d 312, is about 12 micrometers. How long does it take to crawl 12 micrometers? I suspect it can do it in an hour. And this happens throughout development. And there's some reports that this myelination process continues on into early adulthood. And that probably many of you in this room are not completely myelinated yet. That you probably won't be myelinated until you're in your mid to late 20s. So we continue this process of laying down the insulating layers throughout the initial parts of our lives. There's a question. Did I cover all the questions here? Okay. Yes.
So you said that the cytoplasm then kind of gets like squished out?
It gets squished out.
Does it get stored in the cell body, or where does it go?
I don't think it gets stored anywhere. I think it's just because the cytoplasm is constantly changing. It's just, it's being squeezed out, so we have a very, very thin layer of cytoplasm. I don't even think there are any microtubules in there, as far as I know. Someone knows this. I don't know off the top of my head. If you look in that cytoplasm, do you see organelles? I don't think you do. I think that's why it's called compact myelin, because it's basically just, it's one layer of phospholipid bilayer after another with very thin layers of cytoplasm in between. But that cytoplasm doesn't seem to be like the cytoplasm we normally think about. It doesn't have an endoplasmic reticulum, as far as I know. It doesn't have much in the way of ribosomes or much in the way of transport machinery. There's probably some. But as far as I know, there's not much in there. Someone knows this. If you look it up, you'll find it. I don't have a good answer. Yeah?
I'm guessing these cells die eventually, so is there some maintenance throughout our lifetime of these needing to be replaced?
So the question is a really good one about replacing these cells. Yes, they can replace themselves. It doesn't look like there's a constant turnover of these cells. Neurons turn over very little. There's some argument about some areas in the hippocampus where you might get some turnover of neurons. That seems to be clear. But for the most part, neurons don't turn over. You pretty much have the same set of neurons now. You probably have fewer of them than when you were born, but you have pretty much the same set. It's a downhill run throughout life for neurons. These are pretty much the same. You don't replace these a lot. Now, I'll tell you a little bit later when we get to the function of the oligodendrocytes. There are diseases that destroy these. And the diseases that destroy them then will affect electrical signal propagation in the neurons. We can regenerate those oligodendrocytes to some extent, but each time we have a round of this degenerative disease where we destroy the oligodendrocytes, the recovery isn't complete. So it's considered to be a progressive disease because of the destruction of the oligodendrocytes. So it's not like epithelial cells where we have more or less an inexhaustible supply of stem cells that we can generate new epithelial cells. There's probably a finite number of these. And as far as I know, there are not stem cells waiting in the wings to come back and move in. Now, the astrocytes, I'm suspecting that the astrocytes have some ability to replicate. And I'm out on a limb here. But I think the reason I'm saying this is that one of the really dangerous cancers are astrocytomas. These are astrocytes that start to divide. The division gets out of control. We have a very difficult time treating these diseases because we don't have good access for chemotherapeutic agents inside the brain because they're separated by the blood-brain barrier. And these gliomas are really dangerous. I mean, that's what killed John McCain. That's what killed Edward Kennedy, were these proliferating astrocytes. It's a brain cancer. So I'm thinking the astrocytes retain some ability to divide, but I'm judging that from the fact that they can become cancerous. I've not read anything that says that they're continually dividing and replicating themselves. Anything else? Yes?
I need clarification on one more thing. So the oligodendrocyte wraps itself around the axoplasm, and then once it's completed, that's considered myelation, or something happens to the cytoplasm of the oligodendrocyte that becomes myelin. That's correct.
Oh, okay, so let's see if I'll try to answer my question. Answer your question, and when I fail, let me know, and we'll try again. The leading edge goes round and round and round. Okay, And then at the end of it, I think your question is, how do we stop this? Then presumably there's some kind of signal that says stop growing. That seems to be the end of myelination. And what we're left with then is this tiny sliver of cytoplasm bounded by the plasma membrane. And so we have layer after layer after layer of plasma membrane, which is providing the insulating factor to insulate electrical signals from the inside to the outside. Did that answer it?
Yeah.
Okay.
I thought there was some sort of transition. Like when you said the cytoplasm leaves, that's what confused me. Like at some point the cytoplasm transitions to a myelin, but you're saying once it's settled, it's myelin.
Right. And the myelin is in fact the phospholipid bilayers of the membranes of the oligodendrocyte. Okay. Anything else? Yeah.
When does this process start? Does it start before the board or how?
Say that again, please.
When does it start? When does this
Oh, when does this start? This starts during embryonic development. So this is probably going to start pretty much fairly quickly after you set up your nervous system. So I'm guessing this is going to be well within the first 6 weeks. And so that's when it starts. And then it continues into early 20s, late 20s. But that's the finishing touches. You're pretty well myelinated by the time you're I think probably 10 to 12. Yeah.
You might be getting into this, but so what effect does myelination have on the conductivity of the cell?
I'm going to get into that, and I'm going to get into that in great detail. But before we enter that, let me take this image where the axon's oriented this way and turn it this way. And we're now going to look at it much more like we see it above. And I'm going to draw the axon membranes as two parallel lines. Remember, they're going to be a cylinder, but they're going to be two parallel lines. And then I'm going to ask the question, what does this myelination look like on the longitudinal axis of the axon? And the long and the short of that is going to be, we're going to run these for about 1 millimeter or so. Then we're going to have a break. And then we're going to run them for 1 millimeter or 2, 1.5 millimeters, and then we'll have a break. And those breaks are going to be called nodes of Ranvier. And that's where we're headed now. Now, I'll mention it here, but we're going to drill down a lot farther when we talk about signaling. And we'll see that the signaling is primarily occurring from node to node. So that's to answer your question. But let's make a drawing and see if we can work our way into it a little more slowly. So there's the cross-sectional view. Oh, goodness. Okay, let me draw this and then I'll give you a break. So we're simply going to draw the axon, rather than showing it as a circle, we're going to imagine it as a cylinder. But we're going to draw it as two parallel lines. We're going to use this convention a lot. And as we draw it as two parallel lines, I want you to think about how those sequential wraps of myelin are going to be organized in this longitudinal view. So in our simplified drawing here, these are the plasma membranes of the axon. And then again in blue, we're going to imagine what those myelin wraps would look like in this orientation. And what we see is they look a little bit like an onion, where each of these blue lines is meant to be a phospholipid bilayer, or plasma membrane, of the oligodendrocyte. And we see that they extend along the axon a distance of about 1 to maybe 1.5 millimeters. And then there'll be another one here. And then there'll be another one here. Put another one down here. Now you notice what I'm doing. I'm leaving gaps in between each of these oligodendrocytes. Put one here. I think it's easy from the upper view to see how that's an individual cell. Well, this is just a different view. This is also an oligodendrocyte. But every millimeter or millimeter and a half, there's this naked region of the axoplasm. I'm sorry, a naked region of the axon membrane, the axolemma. And this naked region of the axolemma, this site here is called the node of Ranvier. This is another one of these unfortunate eponymous names. Ranvier was a 19th century pathologist who was interested in the nervous system. He worked in Paris. For whatever that's worth, we're now stuck with his name for these gaps because he found them and named them. But what I want you to recognize is the node of Ranvier is naked / exposed plasma membrane of the axon or the conductal region. Now, I'll mention it here. We'll drill down and we'll talk about the mechanisms when we get to it a little bit later. But what we're going to find is the electrical signals. Electrical signals called action potentials. Hop from node to node. Now, they don't literally hop node to node. Electrical signals are going to pass through the cytoplasm. We're going to talk about that in detail. But this term for hopping from node to node, sometimes known as saltatory conduction. And this mechanism, this trick of myelination, can increase action potential propagation by about 100-fold. So it's a trick to make signals propagate along axons much, much faster. I'll tell you probably tomorrow how that gets done. But for now, just recognize that the role of the oligodendrocyte is to increase the rate of signal propagation. And hold on to that idea. Let me finish here, then I'll let you go, and then we can look at some slides. Where I want to finish is that there is a disease of the oligodendrocyte. And the disease of the oligodendrocyte is one we're all too familiar with. It's called multiple sclerosis. Multiple sclerosis seems to be an autoimmune disease. And for reasons we don't understand, something breaks down in the tight junctions between the endothelial cells forming the capillaries in the brain. And for reasons we don't understand, then the immune system now has access to the cells in the nervous system. Normally there's no access of the immune system into the nervous system. It's said to be immune privileged. So we don't get antibodies, we don't get immune cells into the central nervous system. But sometimes things break down, a mistake is made, and the immune system now has access to the central nervous system. And in those cases, T cells have access to oligodendrocytes. And a terrible mistake is made where now these immune cells, which normally never get into the central nervous system at all, begin to destroy the oligodendrocytes. So in fact, this multiple sclerosis is said to be a demyelinating disease. It's demyelinating in that your own immune system is destroying the myelin wraps, destroying the insulation. And when you destroy the insulation, now you impair the ability of these neurons to conduct signals from one place to the next. So you basically are, eventually those neurons will die. But initially, you're impairing their ability to conduct electrical signals. So you don't want to lose these myelin wraps. There was a question earlier about whether or not these oligodendrocytes are with us for all of our lives. And the answer is they better be, they should be. But it's not immutable in the sense that when individuals have multiple sclerosis, they'll have a bout. It's usually called relapsing and remitting. And so they'll go into remission and they're okay. And then they'll have a relapse. And their immune system, for reasons we don't understand, maybe there's some stress, who knows, immune system gets out of order and begins to attack these again. So every time you have a relapse, you're destroying the oligodendrocytes. But the oligodendrocytes have an ability to regenerate. They can find their way back after they've been destroyed and after the immune system takes a break. Then these oligodendrocytes can find their way back and do another round of wrapping. It's just every time they do that, they don't do it as well as they did the first time. So it's a degenerative disease, and eventually the oligodendrocytes will die. And eventually you do lose the myelination. And the final word on this is right now, and I think we'll get better at it, but right now the way we're treating these diseases is we're trying to hold people in remission as long as possible. And if you look at individuals with multiple sclerosis, if you can separate the times when they have another attack by years, the prognosis is quite good. But in some cases, there's a particular variant of the disease, we don't understand why, and it occurs every few weeks or every few months. If you end up having a relapse into the disease every few weeks or every few months, the prognosis is not good. But if you can spread out the time, if you can prolong the time intervals between the relapse, then you can get pretty good lifespans. And so right now the treatment is to hold people's immune system. Once they start to get an attack and their immune system starts to get out of order, we suppress the immune system. So it's pretty serious because now you've taken away the person's immune system, but it's better than destroying the oligodendrocytes. Now, I'm on a limb here, but I'm pretty sure, I wouldn't be surprised if in the next few years we don't find a series of drugs which are going to be able to control this. And the reason I say this is we now understand the immune system so well. We know the switches that are turning cells on and off. And we can now make monoclonal antibodies that recognize those switches and affect those switches. If you watch TV and you see an ad for Humira, that's a drug. I think Humira is one of those. There are a number of them are. And they are drugs for rheumatoid arthritis. Rheumatoid arthritis is an autoimmune disease where your immune system attacks the cartilage in your joints. And we're getting pretty good at controlling that because we know the switches to turn off the cell types that do that. There are another round of drugs that can protect you from cirrhosis and psoriatic arthritis. That's again an autoimmune disease. We know the switches. We can turn those cells off. Some risks, but you can turn those cells off. And I think eventually we're going to find what the switches are for these immune cells that are getting out of regulation to cause the disease of multiple sclerosis. I think we're going to find a way of controlling this disease because we understand the immune system. We'll see. But I'm sure this is not a deep thought. There are a lot of people working on this problem and this solution. So I wouldn't be surprised if we don't see one in the next few years. We'll see. With that, let's take a break. Are there any questions before we go? Yeah.
What was the name of the cells that can turn the switches off?
I'm not sure which cell type turns the switches on and off. They're making monoclonal antibodies to proteins. There are particular proteins that are important in the switches. And most of these treatments that are regulating these autoimmune diseases are targeting the proteins that are important for the switches. So they'll make monoclonal antibodies and disable those proteins that are the switches. Anything else? Well, let's take a break. We'll come back and show some pictures, and then we'll get into electrical signaling. 2. So what we're looking at here is a diagrammatic representation of an astrocyte, but it summarizes, even though it's pretty crude, it summarizes what the astrocytes are intended to do. And down at the lower part of the panel here, it's showing an extension of an astrocyte. It doesn't show it surrounding the synapse, it will. But the point it's making is that this axon terminal, this output region of this neuron, is releasing the neurotransmitter glutamate. The glutamate then binds to glutamate receptors to activate the postsynaptic cell. We're going to talk about that. But the problem in the central nervous system is that these regions are so small, and there's so little extracellular space that we now need to have someone mediating that space, and that's the astrocyte. What it's doing is it's taking up the glutamate out of the extracellular space to regulate the concentrations of glutamate in this narrow gap. The other thing it's doing is it's not shown here, but it's regulating potassium ion concentrations particularly, and also sodium. And we think that it may be pumping the potassium out into the blood system in order to maintain steady concentrations of extracellular potassium and sodium concentrations. This next image is one, I just think it's pretty, it reminds me of the Starship Enterprise, but what it's meant to represent is this is the oligodendrocyte with its nucleus. In the central nervous system, this is a detail, in the central nervous system what will happen is the oligodendrocyte will send out processes that will surround or ensheath or enwrap several axons. In a moment I'll tell you this is not true for the Schwann cells. But now these are the wraps around the axons, and this is the myelin sheath. This is a crude This is a crude animation. This is a Schwann cell, but it's the same idea. And in a moment, this will start, and this is going to start showing how it winds its way around the cell. And each time it winds its way around the cell, it leaves behind these phospholipid bilayers, which form the myelin. This is just an animation of what I drew on the board. And in the end, you end up with all of these phospholipid bilayers of the membranes of that oligodendrocyte. And this is actually an image. This is an electron micrograph. What you're looking at here, this is a cytoplasm. It's pretty well emptied out. These structures are the microtubules. There's a little bit of actin right along the inside. This is the membrane here of the axon. And right outside is the membrane of the oligodendrocyte. Usually right down on the membrane there's a little bit of cytoplasm for the oligodendrocyte. And if you could follow this back round, you would follow it into all of these individual phospholipid bilayers, and each one of these, if you're close enough, you could see there's a narrow space. That's the compact myelin. The cytoplasm has been squeezed out, separated by the black lines, which are the staining, represent the staining of the phospholipid bilayers of the membranes of the oligodendrocyte. So that's basically what we've been talking about. And before we end this discussion of the glial cells, I want to spend a minute talking about their cousins in the peripheral nervous system, and that is the Schwann cells. And we can cover this fairly quickly in that the Schwann cells are the glial cells of the peripheral nervous system. So we're talking about neurons in the central nervous system, the brain and spinal cord. That's all astrocytes and oligodendrocytes. But here we're talking about the peripheral nervous system. And these Schwann cells play the role of myelinating axons in the peripheral nervous system. The story is the same. The distance between the nodes of Ranvier is about a millimeter and a half. They wrap around the axon just as we saw with the oligodendrocytes. They form those insulating layers. They increase the rate of propagation in the peripheral nervous system. They do all the same things. But there's an interesting distinction I want to tell you about between the Schwann cells and the oligodendrocytes. The Schwann cells, these guys will support neuronal regrowth. If you don't damage neurons too badly in the periphery, they're reasonably good at finding their way back to their old targets. The story I tell is one left over from years ago. It was when I was a postdoc. And we were moving the lab. We were moving the lab from where we were at NIH, and we were moving it up to Woods Hole. And so we were packing boxes. I vividly remember it was late at night. I was really tired. And we had this fiber tape. And I remember putting the fiber tape down on a box to seal it. And rather than having one of those really nice fiber tape rolls that had the serrated edge where you could tear it, this was just a roll of fiber tape. But of course, around the lab, there were any number of sharp objects like number 11 scalpel blades. If you've ever seen a number 11 scalpel blade, it has an exquisitely sharp point, and it's very, very sharp, literally razor sharp. And I remember pulling out the tape, taking the number 11 scalpel blade, thinking I was going to cut the tape, and cutting my thumb right there. And I thought, oh, this could be bad. But it was a great anatomy lesson. Because immediately my thumb went numb right to the midline. And the way the nerve comes up here, it innervates right to the midline. And it was absolutely numb to the midline. And it remained that way for, probably 6 months. But over time, it reinnervated, and everything is fine. It's perfectly normal. Those nerves, even though I probably didn't cut them completely, if I'd really severed that nerve, it probably wouldn't have done this, was able to find its way back into the old sheath and work its way back to the original sites and innervate the original sites, and it's perfectly fine now. So the long and the short of it is the Schwann cells support neuronal regrowth, but if we look at oligodendrocytes, oligodendrocytes inhibit neuronal regrowth. What this means, the upshot of this means if we damage neurons in the central nervous system, they don't regrow. This is a big problem because any number of people every year are in car accidents or have gunshot wounds or any number of things, and there's damage to neurons in the central nervous system. Once those neurons are damaged, they can't regrow to their old targets. And the reason they can't regrow to their old targets is because the oligodendrocytes have proteins on them. They're proteins, they're surface proteins that inhibit regrowth. In fact, one of those proteins has the name of no-go. And this is a problem because spinal cord damage or even brain trauma, once we break these axons can't regrow to their old targets, so it's a permanent disability. And it's a story I like, so I'll tell it to you, even though I don't have time. There was a fellow, this must have been in the mid-70s, it was some time ago now. He was working at McGill, he was a neurosurgeon at McGill, his name was Aguayo. And he reasoned, he knew this. He said, well, I know that neurons regrowth can be supported in the peripheral nervous system. And I know it's a problem in the central nervous system. But I have an idea. So he did an experiment. And this is going to be a rat. There's a nose, foot. Rats have a tail. So there's an eye. And so what he did is he cut the spinal cord. And then he reasoned that if he could get the neurons to regrow in a kind of bridge, so he cut the kind of spinal cord and then he formed a bridge of peripheral nerve. As I recall, he used the sciatic nerve. And he basically took that sciatic nerve, I'll put that in blue, and he patched it in on the cranial side of the cut over to the caudal side of the cut. And sure enough, neurons entered this peripheral nerve. They entered this peripheral nerve, grew in the peripheral nerve, re-entered the central nervous system, and stopped growing. It was a tremendous disappointment because he thought he had a way of rewiring the nervous system. But you can't simply extend central nervous system neurons into a supportive environment and have them grow back to the right spots. There's probably real logic for that. During development, you want your neurons to grow out, form their targets, form the final targets, and then you're going to solidify that wiring. You don't want throughout your life to have neurons growing willy-nilly all over the place. So there are mechanisms to keep these neurons from regrowing here, there, and everywhere. And those mechanisms to prevent regrowing are largely proteins on the oligodendrocytes. This problem of getting regeneration in the central nervous system is one that people have been approaching for nearly 50 years now. And the progress has been limited because we haven't figured out a way, first, to prevent the effects of these oligodendrocyte proteins from preventing regrowth. And secondly, and probably more importantly, we haven't figured out a way to guide those neurons back to their old homes. There are signals apparently in the peripheral nervous system which allow these neurons to go back to their old sites when they regrowth, like when I cut the nerve in my thumb. But in the central nervous system, there don't seem to be those signals. So how we're going to solve that problem, someone will solve it eventually, but it's a difficult problem. How we get neurons to regrow, and then subsequently, how we get them back to the right targets. That's an enormous issue. And someone eventually is going to solve it, group of people probably, but it's a hard one. So any questions on that? Yeah.
So the whole idea of neuroplasticity then is rewiring of existing neurons?
The question, great question. The whole issue of neuroplasticity occurs at the synaptic level. We think that when we have plastic brains, we're not having neurons growing millimeters to a new home. When they do that, things break, things go bad. What we think plasticity is local rearrangements of synaptic contacts, strengthening of synaptic contacts. So where before we may have had 1 or 2 synapses between a presynaptic neuron and a postsynaptic neuron, now maybe we have 8 or 10 or more. So it's a change, plasticity is a change in the synaptic configurations and contacts. It's not a change in the number of neurons, nor does it appear to be a wholesale change in connectivity. It's local connectivity. The dendrites with the output regions. Anything else? Okay. Then, a little bit lately, let's get started on the membrane as a battery. What we're going to do here is we're going to do a thought experiment. And if you understand the concepts in this thought experiment and the role of changing the ratios of ions, that's all I'm going to ask about. But some of you will go on into other neurobiology courses, and I want to walk you through some of the nuts and bolts of it so that it doesn't seem entirely foreign if you face this in another class. So we're going to begin with what I'm going to label here as concepts of the membrane potential. Specifically, what we're going to be talking about here is something known as the potassium battery. A battery separates charge, it stores charge, and that's what we're going to do here. And the way I'm going to think about this is I'm going to take this membrane. That's a membrane. There's a membrane here. This is going to be inside. This is going to be outside. Now I'm going to, in this imaginary system, I'm going to add ions. Now, biology doesn't do it this way, but to understand the potassium battery, I think it's easiest to do this one step at a time. And so what we're going to say is we're going to say that on the outside of the cell, potassium on the outside, is equal to 10 millimolar. Now you remember that's not the number I gave for biology, but I want to keep this simple, so we're going to say it's 10 millimolar. Then we're going to say on the inside here, we have potassium concentration on the inside, which is in the neighborhood of about 100 millimolar. In other words, we have 10 times more potassium on the inside than on the outside. And then across the membrane, and I'll put these in orange. Now I'll put them in red. Across the membrane, I'm going to put channels. And I'm going to label these as potassium leak channels. These are potassium selective channels. Now, just where we are now, see what's happening. We have 10 times more potassium in the inside than in the outside. This effectively, the outside can be the ocean. It's an enormous volume. So what's going to happen if we simply put 10 times more potassium on the inside than the outside, and then open pathways for the ions to move? Yes?
The potassium will want to go to the outside?
Potassium will leave, exactly. Potassium will run down its concentration gradient. Let's go from region of higher concentration to regions of lower concentration. And it wouldn't take very long before this 100 millimolar potassium in the inside was simply diluted into the ocean around the cell. But now we're going to invoke another set of characters that will prevent that from happening. What we're going to do is on the inside of the membrane, we're going to put a series of what I'm going to call A negatives. And we'll label these as impermeant anions. These can be proteins, they can be organic acids, they can be any number of things. But the important idea is that they're negatively charged, and they're too big to pass the membrane. Because they're too big to pass the membrane, they're stuck. They're on the inside. So now we start the process again. We have 10 millimolar potassium in the inside, 100 millimolar potassium in the outside. Potassium starts to move down its concentration gradient. It starts to move from where it's in high concentration to where it's in low concentration. But now remember the charge on the potassium. Remind you that this is K plus. So this has a positive charge, the anions have a negative charge. So conceptually what you can imagine here is as the potassium flows down its concentration gradient, it reaches a point where the large negative anions are placing a brake. The electromagnetic fields on the large negative anions and the potassium ions are offsetting one another, and now these potassium ions are being held in place. Their movement is being held in check. It doesn't take very many of these ions to move before we reach an equilibrium. We reach a kind of an equilibrium where the tendency for potassium to leave down its concentration gradient is balanced. So let's see. It's balanced by the electrical charge difference. Holding the potassium ion in place. So we've reached an equilibrium. And we can describe this as the equilibrium potential for potassium. So the equilibrium potential for potassium is simply reached as potassium goes down its concentration gradient, but its movement now is held in check is braked by the negative charge on the large negative anions. That generates the equilibrium. That's what I want you to hold on to. But there's another important part of this that I want to delve into, because it tells you why changing the extracellular potassium concentration has such a big effect on the equilibrium potential for potassium. So if there are no questions on this conceptual thing, I'm going to throw an equation at you. Okay, so the next thing I want to tell you about, I'll do that in the upper panel. And let me say in the beginning, many of you are afraid of mathematics, and I'm going to try to keep this really fundamental. And what I'm going to talk about here is something known as the Nernst potential. And we're going to use it to calculate the equilibrium potential for potassium, EK. This is an equation that was worked out in the late 19th century. And if you get down into the physical chemistry of it, if you're a chemistry major and you get out in the physical chemistry, this is all based on the Boltzmann equations, comes out of statistical mechanics, derived in the Boltzmann equations. We're not going to get into that. But Walter Nernst recognized that he could calculate for any ion, in this case potassium, he could say the equilibrium potential for an ion was equal to a series of constants, RT over ZF. R is the gas constant. T is temperature in degrees Kelvin. Z is the charge on the ion. And F is the Faraday. Now, if you want to know, this is a constant, it's a gas constant, something Boltzmann worked out. T is just degrees temperature. Z is simply the charge, +1, -1, +2, what have you. And F is a means of converting charge into molar constants, so concentration. It's all that is. That's all more I'll even say about it. But now the RT over ZF, we're going to make that a constant, because we're going to fix the temperature, or gas constant the same, all the rest is going to be the same, is going to be times the natural log, ln, of the potassium concentration on the outside divided by the potassium concentration on the inside. Well, you remember from your math, convert natural log, ln, to log base 10, multiply by 2.72. It's constant. If we work our way through this and we say EK at room temperature, so we plug that in, we plug all the numbers in, EK, this constant, and multiply by, and convert from natural log to log base 10, EK is equal to 58 at room temperature times the log of the potassium concentration outside divided by the potassium concentration on the inside. Well, there's a reason I set those two numbers up there as 10 and 100. Because what I want to say now is that we're going to look at the log of potassium concentration on the outside, which we said was 10 millimolar. It's the log of the whole unit. Log of 10 divided by 100. Because remember, we said the concentration of potassium on the inside was 100. This, of course, reduces to log of 0.1. 10 divided by 100 is 0.1. The log of 0.1 is -1. So that tells us that the equilibrium potential K, EK, is equal to -58 millivolts. We can do that calculation. Now, if you plug in the real biological numbers, if you put the real biological numbers in, this 10 turns out to be like 4 or 5. and this 100 turns out to be about 110. And when you run it through at 37 degrees centigrade, or 30 degrees centigrade, and convert that to Kelvin, and you run it completely through, you end up typically with a number that's in the neighborhood of about minus 70 to minus 80 millivolts. So the equilibrium potential for most cells, for neurons, and muscle, is in the neighborhood of about minus 70 to minus 80 millivolts. It'll vary from cell to cell. It'll vary with a bunch of parameters, but it's typically in this neighborhood. I'll let you go through the numbers of what it actually looks like for 37 degrees centigrade and 4 millimolar outside and 110 inside. But it's going to come out about minus 70, minus 80 millivolts. So that's the way we generate a membrane potential. It's the way we generate the potassium equilibrium potential. There's one more point I want to make here before we leave it. And that is, recognize that this is a log of outside over inside. And I'll let you imagine what happens if these numbers begin to approach each other. So let's say rather than 10 to 100, let's say something terrible's happened and it's 100 millimolar on the outside and 100 millimolar on the inside. The log of 1 is equal to 0. There ain't no difference. What I want you to see from that is that's an extreme case. But if you set the inside at 100 or 110, and then you begin to sort of eke this up from 4 to 5 to 10 to 20 to 20 to 30, because it's a log unit, you have a really big effect on the membrane potential. You have a big effect on the equilibrium potential for potassium. This has fundamental biological and clinical implications, because it means as we change the extracellular potassium concentration in, say, around the heart or in the brain, we're now going to have big effects on the membrane potential. What we'll do tomorrow is we're going to invoke another story, and we'll repeat what we have above, but instead we're going to add sodium. And we'll put sodium on the outside, sodium on the inside. We're going to put 100 millimolar sodium on the outside, 10 on the inside, then ask the question how we can change the polarity by opening those sodium channels. So that's the sort of the presaging tomorrow's discussion. So any questions? With that, I'll let you go then, and we'll start into sodium gradients and movement of sodium ions tomorrow.